Let x and y, x tau x and y tau y be two topological spaces and T x to y be a mapping, then T is said to be homeomorphism if T is bijective and both T and T inverse are continuous. So we first write the definition of homeomorphism. Here T is 1 1 and on 2 and both T and T inverse are exist, and also T and T inverse are continuous. Now we write the one theorem which shows this homeomorphism. Theorem gives this: let x and y be normed linear spaces, be normed linear spaces and Tx to y be a linear operator. Such that Tx equal to y, then first T is homeomorphism, there exist constants m singleton m and capital M greater than 0 such that small m norm x less than equal to norm of Tx less than equal to capital M norm x for all x belongs to x. Okay, now we mark it 1. Now going to proof of this theorem, we start proof now. Let first A implies B. Let T be a homeomorphism. Then T is continuous. Then there exists constant m greater than 0 such that norm of Tx less than equal to m norm of x for all x belongs to x. Okay, since T is bijective, then T inverse exists and T inverse is continuous. This implies that norm of T inverse y less than equal to small m norm y for all y belongs to T. Y, capital Y, okay? For all y belongs to capital Y. Then we is a portion for y equal to tx or x equal to T inverse y. We get norm of x less than equal to m norm of tx. For all x belongs to x. This one is, we marked it, this one 2 and this one 3. So from 2 and 3 we get m inverse norm x less than equal to norm of tx less than equal to m norm x. This implies k norm x less than equal to norm of tx less than equal to capital M norm x. This implies option B hold. Okay. Now we further prove this. B implies A. Okay. B implies A. So we know from 1 norm of tx less than equal to m norm of x for all x belongs to x, and let x belongs to x, then and tx equal to 0 gives m norm x less than equal to 0 less than equal to capital M norm x. This implies norm of x equal to 0. This implies x equal to 0. So T is 1 1. So T is 1 1, and since Tx equal to y, then T is 1 2. Now since T inverse y, Tx equal to y, then T inverse exists, and now m norm x less than equal to norm of tx for all x belongs to x. For tx equal to y or x equal to T inverse y, we get T inverse y norm of this less than equal to 1 by m norm of y. This implies that T inverse is continuous. So T is a homeomorphism. Okay, now we're going to one observation of from this theorem. Observation is this: any linear operator, which is onto bounded and bounded below is a homeomorphism. Now we start a linear operator onto bounded and bounded below is a homeomorphism. Now we start the definition of isometry. Let x dx and y dy be two matrix spaces, and tx to y be an onto mapping. Then T is called isometry if tx ty equal to tx xy. For all xy belongs to x. Now we write this observation. Isometry is 1 1. Number 2. T and T inverse are continuous and T is 1 1 and on 2. T is a homeomorphism. Let xy be non-linear space and tx to y be a linear operator. such that tx equal to y, that means onto linear operator, then t is said to be isometry if norm of tx equal to norm of x for all x belongs to x. Now observation for isometry, norm of t equal to 1. In this previous theorem, T is homeomorphism, but norm of T may not be 1. Okay, but for isometry, norm T equal to 1. Now we're going to definition of equivalent norm space. Okay, equivalent norm linear space. Let x, y be two normed linear space. Then they are said to be equivalent if there exists surjective linear operator tx to y such that m norm x less than equal to norm of txy less than equal to capital M norm x for all x belongs to x and for some positive constant and m greater than 0. Okay, now we're going to equivalent norm on a normed linear space. Okay, equivalent norm on a normed linear space. Let X be a normed space and norm A and norm B be norms on X. Then norm A and norm B are said to be equivalent if there exists small m and capital M greater than 0 such that for all x belongs to x. Now observation: M inverse norm xp less than equal to norm xa less than equal to small M inverse xp for all x belongs to x. This one is the equivalent norm on a normed linear space. Okay, so today we stop here.